In this video, we're going to start chapter 4 of the calculus textbook. So up to this point, we've learned about limits. We've learned about a special kind of limit that's called the derivative. In chapter 3, we learned a bunch of differentiation rules that would allow us to calculate derivatives easily without having to use the limit definition every time. Now in chapter 4, we're going to go over some applications of differentiation. In chapter 3, there were some sections that went over certain applications of differentiation. So section 3.7, rates of change in the natural and social sciences. 3.9, related rates. 3.10, linear approximations and differentials. So these were some of the applications of differentiation. In chapter 4, we're going to go through a bunch of other applications. And in this video, we're going to go through section 4.1, so maximum and minimum values. Some of the most important applications of differential calculus are optimization problems, in which we are required to find the optimal or the best way of doing something. So what they're saying here when they're referring to optimization problems is you have a function. So right now we're talking about just single variable functions, functions of one variable, like y is a function of just x. That function could represent something in real life, like the shape of a can, or the acceleration of a space shuttle, etc. And you want to find maximum and or minimum values of that function. That's an optimization problem. The most optimum is the maximum or minimum value of a function. Okay, so they give an example function here. And if we look, here is the maximum value of this entire function, and here's the minimum value. And so they call this, they give a definition here, that this is the absolute maximum and this is the absolute minimum, which means that for the entire function within the entire domain D of the function, so for any input that you could possibly input into the function, the absolute maximum or maximums, you could have more than one, that x value, they're calling it c, is greater than or equal to all fx for any input. Equal to, because maybe you could have more than one. You could have f of d is equal to f of c, potentially. And a similar idea for the absolute minimum. These absolute maximums or minimums are sometimes called global maximum or minimum. The maximum and minimum values of f are called extreme values of f. Okay, so if we take a look at this graph here, for the entire domain of this function, the entire domain for any x that you can put in, the absolute minimum is f of a here, or a, however you want to look at it. And the absolute maximum is this f of d. But then they also point out that we can think about the idea of local maximums or minimums. For example, at b here, this is a local maximum because the value of the function is max within some interval around b. You know, like from a to c, this f of b is the maximum value. And similarly, f of c here is a local minimum because in some interval around c, so like from b to d, let's say, f of c is a minimum. And so they give a definition here. So local maximums or minimums is when the value of the function is greater than or equal to or less than or equal to the function when x is near the value at that x. In definition 2, if we say that something is true near c, we mean that it is true on some open interval containing c. For instance, in figure 3, we see that f of 4 is equal to 5 is a local minimum because it's the smallest value of f on the interval I. Okay, so if we look here, near 4 or near 8 or near 12 means that if you take any open interval around a value, around an x value, the minimum or maximum value in that interval is called a local max or min. Now you might be a little confused because if we come here, couldn't I say, well, let's take the interval from here to here. What's the local max or min? Well, according to this definition, there is none. And you might say, well, how? Wouldn't this be the min and this be the max? Near C, it means it's an open interval. So the function isn't defined at the endpoints of the interval we specify. So in that case, so let's say this is, 3 to 5, but it's not defined at 3 or at 5, so there is no minimum. You can't say, is it f of 3.1, 3.01, 3.0001? You can't say that there's a minimum or a maximum. Okay, so you're going to specify an interval, an open interval on the function, somewhere inside of the function, and there's either going to be no local max or min, or you'll do something like this. You'll say the open interval from here to here, and now in this case, there clearly there's a local maximum in this case. From here to here, there's a local minimum in this case. Now, notice though that when we talk about a global maximum or minimum, the endpoints, they could be open depending on how the function is defined. It just depends on how the function is defined. But like just looking at this, to define this function, it would be the closed interval between A and the end here, right? The function, like these endpoints are part of the function. This is not an open circle here. So that's why they can say, okay, this left endpoint here is the local or the global minimum. And we don't say the right endpoint is the global maximum because this is larger. Okay, so if you need to rewind the last few minutes of what I was just talking about, because this could be confusing. A function has absolute maximums and minimums, or it might not have an absolute maximum or minimum. We'll see examples of that. But in general, you think about the idea of the absolute maximum and minimum for a function, which is based on the entire domain of the function, absolutely any possible input, the entire domain. What is the maximum value? What is the minimum? That's also known as global maximums and mins. Local maxes and mins are based on some open interval within the function. Open interval. And inside that open interval, there may be a local max, there may be a local min, there may be both, there may not be either. If there is a local max or min at an x value, then the idea is you're calling it local because it's true near C, meaning some open interval within the function domain near C, meaning some open interval within the function domain around C. Okay. Also, they mentioned the maximum and minimum values of f are called extreme values of f. These extreme values include both global and local. The term extreme values is not just applied for global maxes and mins, it's local as well. Okay, so here they give an example of a function cosine of x, and they want to show that you can have more than one maximum or minimum. So 1 here, the value 1 is a local and global absolute min. So they're saying local and global because this is the only local maximum within like this interval, right? But it's also in general, this is the global maximum as well, as long with there's an infinite number of global maximums and global minimums, 1 and -1. So you can have more than one extreme value. Okay, here they give an example of this function. This is y is equal to x squared. It has a global minimum, which is also, you can look at it as a local minimum, however you want to look at it. But there's no global maximum or local maximum. There's no maximums. There's no local maximum because there's no open interval that you can give and you find a local maximum value. But then at the same time, there's no global maximum either because it's like infinity. You can't specify a specific number. Okay, here they point out that this is x cubed, or no, this is x cubed. And they point out that there is no global max or min or local max or min for the entire function. You might think, well, what about this point? Okay, so let's put an interval here, an open interval here. Well, no, I mean, if this was a closed interval, this would be the minimum and this would be the maximum. But when we're doing local maxes or mins, you do an open interval. So there is no max or min, local max or min. Okay, then they give this function here, but they specify a domain, and this is a closed interval, -1 to 4 closed. And So this would be the global max. This would be the global min, which is also like a local min. So how is it also, again, how is it also a local min? Because you can specify an open interval near it or around it, and it's the minimum value within that open interval. But the global max or min, it's not open interval. It's literally any number possible in the domain. Is there a single value that's greater than or equal to all possible values for the function? Yeah, this one. And this one, in terms of this one for max and this one for min. Okay, so we have seen that some functions have extreme values, whereas others do not. The following theorem gives conditions under which a function is guaranteed to possess extreme values. The extreme value theorem. Okay, before we talk about the extreme value theorem, just a reminder, we've talked about one theorem that sounds like this, the intermediate value theorem. That was in section 2.5. Okay, so this was in the section on continuity. The intermediate value theorem said that suppose that f is continuous on the closed interval from a to b, let n be any number between f of a and f of b, where f of a is not equal to f of b, then there exists a number c in ab such that f of c is equal to n. So what they're saying is if you have some function that's continuous over an interval, and the start point of the interval and the end point of the interval aren't equal, right? So f of a is not equal to f of b, then pretty much what they're saying is to draw the function from f of a to f of b, you have to pass through every possible y value that's between a and b, between f of a and f of b. So there's going to exist some number some number that's between f of a and f of b, to where it's going to have an x value that's going to map to that number. This is like a statement of the kind of the meaning of continuity. The idea that you have to, for something to be continuous, you can draw it and you don't pick up your pen off the page. So if the interval from a to b, where f of a is not equal to f of b, if the function is continuous, there's no way to get to f of b without not picking up your pen off the page. That's kind of the idea. There's an intermediate value. Okay, so now the extreme value theorem says that if f is continuous on a closed interval from a to b, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some numbers c and d in the closed interval from a to b. So this definition is a little confusing to me, because it almost looks like, well, first of all, okay, the key words here are the interval is a closed interval, and it's talking about absolute. If you have any closed interval, then there will be an absolute maximum and an absolute minimum. And what's confusing to me is they almost make it sound like you have the absolute max and min will be at C and D, so that implies that these values are different. It must be different from A and B, but that's not the case. That includes the endpoints. And this makes sense. This makes intuitive sense. If you have any closed interval, it must be closed, then no matter what, there's going to be an absolute max and min. Absolute. And so they give 3 examples here. And these, in between the endpoints, all of these have a local max and min. You can see it's these like peak points. That's what a local max. If it's going to be a local max or min, it's going to have to be a peak point, like this. You see how it kind of peaks like that. A peak or valley, a peak or valley. And we just discussed a few minutes ago why that for a local, meaning that open interval, why it has to be a peak or a valley like that. So all 3 of these have a peak or valley, but it doesn't have to have a peak, a local max or min, a peak or valley. You could have, it could just be, because it's a closed interval. Look, there's no peak or valley there, but the endpoints then are the max and min. Now, also notice that this doesn't say that f of a is not equal to f of b. F of a can be equal to f of b. That's not the case here. But so what if I have this? What if we've got f of a is equal to f of b, and you've got a straight line? What's the local max and min there? or what's the absolute max and min there? The global max and min. That's what the extreme value theorem is talking about. The absolute, the global. So what's the absolute max and min here? Well, let's come back to the definition of absolute max and min. So if we had that straight line from the endpoints, closed interval, let's say we're looking, let's say F4. Is F of 4 a absolute max or min? Okay, well, so C is equal to 4. Is F of 4 greater than or equal to all of f of x for any input? Yeah, it is. It's not. It's equal to it is great. F of 4 is greater than or equal to absolutely any value in this domain. What about minimum? Is f of 4 less than or equal to f of x for all x and d? Yes. So f of 4 is an absolute max and min. Every single one of these points in the function is an absolute max and absolute min. And you can think about that, a similar idea with local maxes and mins. It's defined that way, where f of c is greater than or equal to or less than or equal to f of x when x is near c. So like if you had some function that was an open interval and it had like a straight line up there and did that. Well, this plateau here, that's all local maximums. Okay, figures 9 and 10 show that a function need not possess extreme values if either hypothesis is omitted from the extreme value theorem. So the extreme value theorem specified continuous over a closed interval. Okay, so they're going to omit continuity here. So the interval is closed between 1 and 2, but it's not continuous. So that the theorem is going to be violated, or it's not going to be violated, but it's not going to have both extreme values, or both not as far as absolute extreme value. Look, there's a global minimum here, which is at f of 2, but there's no global maximum because you can't specify a specific number. You can get infinitely close to, this is f of 1, so f of 0.999, a million nines, and you can just keep going to infinity. You can't specify a specific number. It's open here. Okay, here it's continuous, but it's an open interval, and you can see that there's definitely no global max because you can get infinitely close to 2, and it looks like there's no global min either. But maybe because you're getting into that, it looks like it's maybe it is a valley. Let's see. The function g shown in figure 10 is continuous on the open interval, but has neither a maximum nor a minimum value. Yeah, you can get infinitely close to 1, but it doesn't, f of y or y of x it never equals 1. It just gets infinitely close to 1 coming from the top. Okay, the extreme value theorem says that a continuous function on a closed interval has a maximum value and a minimum value, an absolute maximum and minimum, but it does not tell us how to find these extreme values. Notice in figure 8 that the absolute maximum and minimum values that are between a and b occur at local maximum or minimum values. So we start by looking for local extreme values. So yeah, how do we find extreme values? Either global or local extreme values. Okay, well, one theorem that we can use says that if f has a local maximum or minimum at c, and if f prime c exists, then f prime of c is equal to 0. Where does this come from? What they're pointing out is that if we're dealing with a local max or min, we've talked about so far that it has to be one of those peaks or valleys. There's no other way to have a local maximum or minimum when we're talking about those open intervals. Well, what do we know? What can we see when we look at this peak and this valley? Look at the tangent line. It's horizontal, so the slope of the tangent line is 0. So what they're saying is if we have a local maximum or minimum, which remember could also potentially be global as well. It could be both local and global. If f has a local maximum or minimum at a point c, and if f prime c exists, then f prime of c is equal to 0. Okay? Now, they specify that f prime of c it must exist because we're going to talk about this, but remember we saw an example where we could have a local max or min, but the derivative doesn't exist. But what we've seen, though, is that what this theorem is saying is that if there is a local maximum or minimum at c, if there is one, and the derivative does exist, then that derivative will be equal to 0 at that point. That's a fact. But, okay, so they point this out, though, because we want to look at that theorem. We want to make sure we understand that theorem. Here, this is x cubed. The derivative at x is equal to 0 here is equal to 0. But that we talked about, this is not a local max or min. So did that violate this Fermat's theorem? No. The theorem said if there is a local max or min and the derivative exists, then that derivative is going to be equal to 0. The theorem didn't say if the derivative at a point is equal to 0, then it's a local max or min. You see, it didn't say that. Okay, then they also point out that here's an example where we have a local minimum, but the derivative doesn't exist. Okay, so what we're trying to do right now is develop a method for finding extreme values on functions. That's what we're trying to do. That's how we're going to answer optimization problems. So either local extreme values or global extreme values or both. That's what we're trying to do. And what we can see so far is that we can take the derivative of a function and find the values of x where the derivative equals 0, and find the values of the derivative where the derivative doesn't exist. And potentially we'll need to do more work. We'll need to check. Potentially those will be local extreme values and also maybe global. We'll have to do more work, though, because we can see the derivative equals 0. That's not an extreme value. We know there's other, we know that there's points where the derivative doesn't exist, and it's not an extreme value like a vertical asymptote, but still points where the derivative is equal to 0 or the derivative doesn't exist. We want to know if we're trying to find extreme values. That's a starting point. So that's where this definition comes from. A critical number of a function f is a number c in the domain of f such that either f prime of c is equal to 0 or f prime of c does not exist. Okay, and then we can have multiple points on the same function where f prime of c is equal to 0 or f prime of c doesn't exist. Okay, that's critical numbers. And again, though, this does not mean that once we find the critical numbers, we've found the extreme values. We'll have to do more work. Okay, so find the critical numbers of f of x. We're going to work a bunch of example problems, but all they're doing is finding this derivative, setting it equal to 0, and solving for x. And they do this, they get x is equal to 3/2 and 0, because the derivative doesn't exist when x is equal to 0, and the derivative is equal to 0 when x is equal to 3/2, and you look at the function here. Yeah, see that horizontal slope at 3/2, and at 0, you've got a vertical tangent. So this is not an extreme value. The derivative doesn't exist here, but this isn't like what we saw here. This is just a vertical tangent, but this is an extreme value. This is a local and a global extreme value. If f has a local maximum or minimum at c, then c is a critical number of f. Yeah, I mean, this is what they've explained to us so far. This is what we've talked about. There's no way to have, well, okay, no, you can have, I'm not sure what they're going for here. I mean, yeah, so if f prime, there's no way to have a local maximum or minimum where the derivative exists and it's not a horizontal tangent. We've seen that. And then you can have the derivative not exist and have like a kink point, but if it's a local minimum, yeah, I'm really not sure what this is saying here. I guess this is just like a definitive math statement. To me, this seems like just stating the obvious based on what we've learned so far. To find an absolute maximum or minimum of a continuous function on a closed interval, we note that either it is local or it occurs at an endpoint of the interval. The closed interval method. So what we can see is that if you're looking for, like we're starting with, okay, well, let's say we have a continuous function over a closed interval. This is like the simplest case, continuous function over a closed interval. And you want to find the absolute max and min. What do? Find the critical numbers on that interval, and then also write down the values of f at the endpoints, because it's a closed interval, right? It's the endpoints are included. The largest values from steps 1 and 2, that's the absolute maximum value, and the smallest value is the absolute minimum value. That's easy. Now, they're not really specifying, well, like, what if one of your critical numbers was like x cubed? What if one of your critical numbers is here? Well, you don't need to be concerned with that, is what they're saying. Just write down the critical number, note what the value of the function is at that number, and if it's a point like this, then it's not going to be the largest or the smallest. So you're not concerned with that. They're just saying you could have a function that does all kind of stuff, has a kink point here, you find all these critical numbers, you find the values of the endpoints, and just compare and just find what's the largest of all those numbers. And this is another critical number. You'll find what is the value. Let me do this. Okay. So you've got, okay, so you would get all the critical numbers. You have a critical number here, here, a vertical tangent here. The derivative doesn't exist. A horizontal slope here doesn't exist. But this is not a local max or min. This is just a horizontal slope. But it doesn't matter. It's gonna be a critical number. You'll just compare all of the numbers, and you'll see, okay, look, there's your global min, and then your global max would be here. Later we're gonna talk about how we can, once we have a critical number, we can analyze to see is that a local max, a local min, or neither. Okay, so that now they find the absolute max and min. We're going to work a bunch of examples. The Hubble Space Telescope was deployed on April 24th, 1990. A model for the velocity of the shuttle during the mission from liftoff at t equals 0 until the solid rocket boosters were jettisoned at t is equal to 126 seconds is given by this formula. Using this model, estimate the absolute maximum and minimum values of the acceleration of the shuttle between liftoff and the jettisoning of the boosters. Yeah, so we're going to work examples, but how do you find on the interval from t is equal to 0 to 126? It's a closed interval. What's the maximum and minimum, absolute maximum and minimum values? And then what they'll do is they'll find, okay, well, what's the acceleration at those values? No, they would take the derivative first and then analyze the acceleration function, but you get the idea. You can take any function, and now we see with what we just learned in this section is that we can take any function, and I'm going to say over an interval because a lot of times it doesn't have to be over an interval. It could be for whatever you want, all numbers in the domain, whatever you want, and you can analyze definitively what's the absolute max and min. We just learned how we can do that. Now, we haven't really talked about, well, how do we find exact values for local maxes and mins? How do we determine if, in fact, we have a critical number that is a local max and min? We're going to get to that in upcoming sections, but right now we can identify for sure for a function what is the absolute max and min for that function, maybe overall for all the entire domain over a specified interval. And so that's useful, right? That's what we could do for this velocity function. That's what we could do when they take the derivative for the acceleration. What is the absolute maximum and minimum acceleration over that time period for time t equals 0 to 126? Now you might be saying, okay, well, wait a minute. This was for specifically for the closed interval. What about an open interval? Well, okay, You just, okay, like this is an open interval, but maybe one side's closed, one side's open, whatever you want. There is no global minimum now, but there is a global maximum. This is the global max. This is still the global max. Or, okay, you could do this. You could say, let's say this was the acceleration for the rocket. We'll just take the limit as x approaches this, and you can treat that as your global minimum. That would be your minimum acceleration. Just take the limit. Okay, so now let's just work some example problems, and you'll get the feel for this.